All right, good afternoon. Welcome to our 2025 first Q&A session on A World from Dust, chapters 1 through 3. So I want to tell you, and let me call up the first screen on this. Thank you for your questions, and thank you for getting them in on time. That allows me to do the video today. And the other thing I'd like to mention is that these are really good questions. They're very open-ended. And so what I say right here is not the final word, but it's how I went to the literature to look up what I think a best answer would be to the question. So it's not just me talking, it's the literature talking. At the end of class, you are going to be giving presentations like this, where you're going to be talking about an overall metal involved in the entire story of chemical evolution. And so I'm going to want you to do something like this. In fact, if you remember one of these that I answer your question with and you want to go back and look at that and just tell me a little more about it, that'd be a really good way for you to get one of your two papers that you're supposed to have for that final presentation. That's a long way away. Let's get to your questions so I can tell you what the preliminary answers are and how they open up the way to asking more questions. So really good questions. So let's start with these. We're turned in roughly in order. Thomas has a very good chapter 1 question. If arsenic, we talked about how arsenic wasn't suitable for the DNA backbone. Could it be antimony? It makes sense because you moved down from phosphate to arsenic, and there was a possibility for that working. Moved down from arsenic to antimony, and maybe that would work as well. It's even the same kind of category. It's the yellow semi-metal category right here. Same column in the periodic table. Should be similar electronics, but it does have 5 valence electrons. The other thing I'd like you to notice about this, though, it is in the same column, but notice that some of these periodic trends, they go toward the corner of the periodic table, not just the right to left property of the periodic table. In particular, like fluorine is so electronegative, things like that have to do with electronegativity will actually be periodic trends in a diagonal direction. What that means is that if you're looking for a replacement for phosphorus, yes, you can move down in the column, but the further you move down in the column, you see that you're moving farther away from the diagonal, if that makes sense. And so it's possible that you could ask this question about selenium, which is actually used in biology in some ways, as well as doing it about antimony. Once you get also in these bigger elements, they start to act different because they're so much bigger. They have so many electrons. Those electrons influence each other. And so antimony does not create a phosphate type molecule, phosphate PO4. That naturally happens in water, and there can be arsenate, which can just plug in. And I guess that's the important thing about DNA. DNA doesn't have a phosphorus backbone, it has a phosphate backbone. And arsenate is possible to form in monolake, but antimonate is not even really possible to form. Your electronic structures have just gotten too different from, you can't do the simple periodic trend all the way down there. So antimonate, SbO4, would be much harder to find. In fact, what you do find usually is something like Sb2O3, because it can bind itself, it can bind other oxygens, and it doesn't do it as 4-to-1 ratio. It does it in a 3-to-2 ratio. So you can get some clues of this. It's actually a really complicated question to ask exactly what's going on, but you get some clues that antimonate is not really preferred because you can't really find it in mineralogy. Instead, you find things like this, which have these kind of arrangements. Look at that valentinite, which is one of the major forms of antimony with oxygen. That doesn't look anything like a tetrahedral PO4. So I think we're just getting too far away from the original phosphate, although it'd be interesting to extend your question to ask if selenate would be a possibility, because if we're moving across a diagonal rather than down a column, maybe that would be a possibility. But I don't have time to look up for that. I'll leave that for you to investigate. Oh, the other thing to mention is that this is aerobic environments, and if you had early Earth, it'd be anaerobic environment, but it gets even worse because that would be antimony 5, which forms Sb2O5. That still doesn't help you form SbO4 in water, which is what you really want. Oh, and the other thing to say is, how do chemists actually make alternate backbones? If they have a choice between anything, you don't have to go with what's just in the lake around you if you're a chemist. You can purify stuff out. Have any chemist tried to make an antimonate or even an arsenate backbone? And one of the key parts of this argument is that no, they haven't really. They haven't. What they've done is they've used organic chemistry, not inorganic chemistry, to make phosphate replacements. There's a peptide backbone that people have tried. So they make PNA, peptide nucleic acid, rather than DNA, deoxyribo. It's kind of a weird form. And one of the things they found is using a morpholino analog, but just look at that. That is just carbon, nitrogen, oxygen. I'm actually not sure what L is, but I think it means ligand or the DNA ladder. I'm not exactly sure why they use L. Obviously, it's not an element. So it's probably something carbon containing. And you can use organic chemistry to develop something that is flexible and has a charge to it. And it can even not look much like phosphate at all. But now we're getting well away from what could actually evolve. This is what humans can do, not what evolution can do. Evolution can make a step where it could use arsenate instead of phosphate. That is a more reasonable hypothesis. It's just that it ignores the chemical facts of what arsenate actually acts like. Good question. Here's another good question from Sam. And this is such a big question. I had to narrow it down a little bit. But again, you can search these questions out for your final presentation. Be thinking about papers like this. Okay, so the question is, how many connections have we made between chemistry of the elements, periodic trends is the way that chemists would talk about that, and the way they're grouped into certain minerals, the way that certain minerals happened early in planet formation. And there's a number of ways that you can go with this. Robert Hazen, you're going to be introduced to him, I believe, at the beginning of chapter 4, if not already. But he is the one who talks about mineral evolution. And so I actually started looking at his most recent paper. It was really cool, but didn't have specifically anything about periodic trends. That stuff is in his work. It's just a little bit below the surface sometimes. I decided to go into a different direction to see how people were asking Sam's questions specifically with a specific chemical property. So, Sam, you listed size, charge, how well they was dissolved, the way they bond, and all these different elements. And so the question is, we've got to pick one. So here's a paper that we found a periodic trend, and they looked at periodic trends of how minerals form under high pressures, like in the core of the planet, and how they relate to their electronegativity. So they focus on one aspect of the periodic table, and it's probably one of the strongest periodic trends, which is electronegativity. We will actually show you, I think that I didn't cut it from the class this year, electronegativity is a physical chemistry thing. And so this is a great physical chemistry question because you're asking about things that are physical properties. The things that you have up there are physical properties. We're going to talk about all of them in class. And so you can find a paper about how do these properties change under different planet formation geological kind of properties, which is a question of how does it change with pressure. And what do you know? We talk about how pressure changes things in physical chemistry. So this is a great question. We just want to narrow it down to a specifically physical chemistry question. Crystal field theory, by the way, is an inorganic theory. So I'm going to keep it physical. I'm going to talk about electronegativity, and I'm going to tell you about this paper I found. Basically what they did is they used machine learning, which is another way people usually talk about that with the broad umbrella of AI right now. But it's machine learning to look at data from different pressures and to compare it to the periodic table and to try to develop a physical chemistry equation. Look at that equation right in the middle of the page right there. It has a funny X. That is electronegativity. And the idea is you're comparing two different metals and you're trying to see which way will the electrons go, which means which one is more electronegative. And does pressure change how the electrons move? Now, of course, you have to deal with a lot of things, and what they're doing is they're using machine learning to look in trends in existing data to try to extend those trends to the entire periodic table. Very cool stuff, in my opinion. But I want to point out that the equation that they're using is a very much a physical chemistry equation. It's actually not that complicated, and it's algebraic rather than calculus-based. That's the good news. Again, we can get by with using less math than you might have expected. And it's a pressure-modulated relative work function. Notice the physical chemistry terms. Pressure is changing. How does work go? And remember, work is something moving, force over a distance. The force in this case is electronegativity applied over the distance between the two nuclei, or the two atoms. And so you have the conductivity, the two metals, the electrons being transferred. You do have a few other things that we don't talk about as much in physical chemistry, but I hope you can see this is really a physical chemistry question. And this is an example of a great paper that would be good for you to bring up at the end of class to sort of summarize for us. One of the things I'll summarize is that they take the different types of metals exactly like what Sam was talking about. With the different groups of metals, do they behave differently towards each other in some kind of way? The groups are organized by the periodic table. So if you find differences between groups, that means you are seeing how the periodic table shapes this electronegativity, which is the exact subtitle of my book. So this goes right along with what we're saying and doing. What they did is they used their machine learning, and they found out there are only 1, 2, 3, 4 numbers that they got out, and then one parameter depending on what is going on, how the charge is being transferred. But they found 4 different parts of the equation, 4 different numbers that the machine learning found out, and they organized them by groups, and you can see there are different coefficients for the different groups. And I put the equation again down here so I can show you that's the main point of what they're doing. They are doing a physical chemistry equation. I could even turn this into a homework problem for you if I wanted to. That means that this is the kind of thing you can talk about the trends they found. The overall trend they found is that pressure increases electron transfer probability. In other words, electrons transfer more easily when they're under high pressures. And that could have an impact on what different minerals you will get in high pressures under the early Earth. And then as the Earth continues, as time goes on, maybe that has an effect on mineral evolution. So I just want to say, Robert Hazen is the big picture person to talk about with mineral evolution. He has a couple of new papers I started to look at. But then I realized we want to talk about physical chemistry. So let's go for a specific question. I want to show you how to drill down on a specific question. Overall, they had the finding of pressure-induced electron transfer happens more. Does that affect different groups differently? And that's the kind of thing that you could dive into the paper and find out what their conclusions are. And so that actually leads to Michelle's question, which also leads forward to Chapter 5, where we really talk about origin of life. But Michelle's question, I just want to show you how to drill down to this kind of question. It's a specific zinc-based question, and it's the question of, could zinc have been a good catalyst for the origin of life? And we're going to have more examples of this going on as we come up to it. But this is the idea we talked about zinc in Chapter 2. And the answer is yes. And you're anticipating a bit of what's going to happen in Chapter 5. But if you've thought about this, one of the questions to ask is, has someone else thought about it and published a paper about it? So I did a couple searches and I found out zinc and the origin of life. There's even this particular author who has written this 2009 article about the origin of life in the zinc world. And why did this author think zinc was a good idea for the origin of life? Specifically, it is a photosynthesizing mineral that could be porous and it could be precipitated hydrothermally. In other words, we'll talk about those more when we get to the later chapters, especially Chapter 5. So you want to hold on to some of these ideas, but the basic idea is, yes, this is exactly what this author is saying, and so you can eventually talk about what they say. They show things in terms of energy and redox potential. And by the way, on Sam's figure, there was redox potential on that. That's going to be a later chapter, but by the time we get to your presentations, you'll have talked about redox potential and energies of where electrons go, the work that electrons do in moving from one electrode to another. That's work. That's physical chemistry. We're going to talk about that. So this is the specific hypothesis that the person is saying that zinc is going to do. And it's important to say it's not just metallic zinc, it's zinc sulfide. Remember that that is an early Earth. There's going to be more zinc sulfide than zinc oxide on the early Earth. And it turns out that zinc sulfide actually will absorb solar radiation and redirect it. And it could even say that you could reduce, this author says, the zinc could absorb solar radiation and reduce carbon dioxide, making biopolymers that can serve, and we can talk about those as you go into it. And those can be the templates for longer biopolymers, and then the zinc could have actually protected the first biopolymers from photodissociation. And so they show you physical chemistry on the left that shows you energies, and shows you reactions. And you want to see how the energies are the electrons moving. And as you want to, if, like Michelle, if you take zinc at the end of class for your presentation, then you could actually use this as one of your 2 papers if you just explain it to us, how the energies work, how the sunlight energy is transformed into electron moving energy by the zinc sulfide. Very cool. And one of the things that the author did is I noticed that they had this where they compare concentrations in modern seawater and blood plasma in the cell cytoplasm, which is exactly the argument that R.J.P. Williams made and exactly the argument that I made in like the solubility stack. And I think that's actually coming up in chapter 4. I don't remember if it's chapter 3 or 4. But basically, this is the exact same argument that's made by one of the figures in the book that shows different solubilities go with availabilities of the element. And I thought, well, that's interesting. There's this is the exact argument that R.J.P. Williams made. And then I looked in the acknowledgments, and he thanked R.J.P. Williams for his in-person discussions about this. So that shows that this indeed does come from R.J.P. Williams. This person was inspired by him just like I was, and you can be inspired by him the same way. You can look at these things, and you can see the high concentration of zinc in the cell cytoplasm is really interesting because it seems to imply that it's important to life. And so what if it's important to the maintenance of life, ongoing life? Maybe zinc was important to the origin of life. How would that be the case? That's the theory that we have right here. This actually goes a little bit with Sam's ideas about what's the different minerals like. Just remember, when you have rocks forming and you have large oceans, then you will have solubilities will start to matter. We're going to talk about solubilities right before test 1. So pretty quick, we're going to be talking about solubilities. It's a big part of R.J.P. Williams' ideas, and it's a big part of physical chemistry. And I just want to end up with the idea of chemistry can really tie all these questions together. This author specifically says that the zinc world scenario that he puts forward can show how metabolism first and replication first can be reconciled and combined. Because biologists will argue, did metabolism come first or replication come first? Well, zinc sulfide can actually help with both. And there's a little bit of this language when you get to chapter 5. You'll come across this idea. It's the idea that there can be 2 hypotheses that look like they're competing if biology is just considered. If you consider chemistry, there is a way that both can happen at the same time from the same chemical element, same compound, that's doing similar reactions that can help both happen. That's what he's saying. And that's actually what you'll see when you get to chapters 5. So, this is great questions. The only thing that I want to say, I think that your connections are all related to your questions, and so that is fine. But if you make a connection that is more like, this reminds me of this thing that happened in a movie, or things like that, or this book, or things like that, the connections can be anything. So I just want to mention, I like all the connections that you all made. Feel free to be more creative in the connections because they're not really necessarily meant to be tied to the questions. But if that's the connection you come up with, that's great too, because these are very good questions. And you can see how we can make more connections to papers in the literature. I want to show you how to do that with this. All right. So this is our first Q&A. Be reading on and be preparing more questions for the next Q&A, which will be chapters 4 through 6, and that will be at the end of April. Thanks for listening.